Hello and welcome to another episode of the Oxford Online Maths Club, a special bank holiday half-term episode on a Thursday afternoon. It's good to be back, and sorry if you missed last week's episode because of tech issues. Exactly 168 hours ago, my internet was completely rubbish 168 hours ago, and it was also completely rubbish 5 minutes ago. But this time I need to check it, I need to keep an eye on it, and this time I fixed it before going live rather than just afterwards. So we're all good. I'm going to live with lots of people in chat. Hi to Casey and Darishle and Ali. Somebody anonymous has asked me my opinions on the Maths and Philosophy course. It's a really good course. It combines maths, actual bits of the maths course. You go to the same lectures as mathematicians for those bits, and study of philosophy, where you get to explore more about maybe the philosophy involved in the overlap, or maybe other bits of philosophy that you're interested in as well. So there's bits of both. It's called a joint honours course. That thing where you study two different subjects. They're not so common in the UK compared to places like the USA, where you might do. It's more likely that you study lots of different things. But Oxford only has very few of these joint honours courses in particular combinations, and one of them is Maths and Philosophy. Bonjour to the person who said bonjour. Darishle also had bad internet last week, and Amelia missed us. So hi, good to have you with us again, Amelia, and also hi to Catherine. Oh, lovely. I thought maybe this would be a really quiet, tiny one because it's half term. And maybe that is true. Also, maybe everyone stopped watching at some point over the last term. You've got exams, it's half term, got other things going on. Hello to this anonymous person as well. If you want to join the live chat, we're over at vivox.com. There's an event code on the screen and in the YouTube description if you're on desktop. But we don't do, as someone here says, we don't do term schedules. I just roll through and we just keep going and see what happens. I hope everyone's well. I hope you're doing good. Today I want to talk about sums and integrals. I've been doing some sort of classic problems recently, and this idea for a session started as a sort of classic problem, but it's not quite the same as what we've been doing for the last, 5 weeks or whatever it's been on classic problems. I suppose we've done 6 episodes in a row on classic problems. This one might feel a little bit different, a little bit maybe more mathsy. I saw some people in the comments complaining that these are getting too sort of logic, physics, stuff like that. Yeah, so I'm going to do some sort of calculations you might have seen before or maybe not. We're going to compare some sums and integrals together. And yeah, hi, thanks Raphael. So far going better than last week. The worst thing about last week was that although the screen stopped broadcasting, the graphics didn't work, the audio still went through. So everybody could hear me complaining about how my tech was broken in a little disembodied complaint machine, which is not very dignified in hindsight. Right, good. Okay, I'm just clicking on buttons, don't mind me. Yeah, it's been quite elementary. Let's make this less elementary. We're going to do some integrals. SV's here. SV likes integrals, I think. Just pointing at people. Okay, the idea is there's this one comparison you can do between a particular sum, something where you add together discrete objects, versus an integral. We're going to do a few of these, but there's one sort of semi-famous one. It works like this. You consider the graph of, this is my xy graph. Consider the graph y equals 1 over x. The theme this term is that I say something near the start which possibly causes people to say, oh yeah, I know where this is going. And then hopefully I try and by the end go somewhere they weren't expecting me to go. So we'll see. There's my graph of 1 over x, y is 1 over x. One of my better ones, I've just put it in the positive xy. So people in chat are also trying to guess where this is going. How easy is it to get 7 at IB Maths? Oh goodness. Versus A star Maths and Further Maths A level. I've seen some stats on this once ages ago. They're supposed to be about the same. I think. This is 2 guesses for Gabriel's horn. It's not Gabriel's horn today. There are plenty of YouTube videos about Gabriel's horn, and also, to be honest, plenty of things about what I'm going to tell you anyway. Here's the sum. Well, this has got kind of squares on it, so that's quite nice. So I would like to draw in some rectangles like this. Okay, I'm going to keep going. This is going to be the number 1, 2, 3, 4, 5, and so on. Maybe I'll call this n, although that might be n equals 6 in this picture. You haven't missed anything yet, Roy. We are talking about this. Jerusalem is also trying to guess what's going on. There's more guesses of what's going on. What happened to Slido? We switched to Vvox at some point this term. It's a little bit experimental. It's got a different setup and it lets me put maths in the polls. I haven't actually used that feature very much, so I keep saying that I can put maths in the polls, but they're never actually putting any maths in the polls. It's a bit embarrassing, really, isn't it? Good, okay. Maybe I shouldn't have encouraged people to guess where I was going with this. Okay, cool. okay. Excuse me. So, right, okay. The rectangles are a series of, well, they've got different areas. This one's got height 1, and then this one's got height 2, height 1 over 2, and the next one's got height 1 over 3, and so on. So the area for the rectangles represents a sum. Let's say I keep going out to, maybe I keep going out to, that's not a great picture, but I keep going out to, I'm going to put an n over here, for big number n. Area of the rectangles is, now let's see. Ah. Sorry, also keeping up with chat. Area of the rectangles is 1 plus 1/2 plus 1/3 plus, and so on up to, I suppose this is 1 over n minus 1 for the last one? Yeah, I think that's true. Yeah, we had an episode about Riemann sums for integration, quite a while ago, about a year ago now, I suppose, if you scroll back through the archives to an episode with Aditi about integration. And we had something, you can, if you make the rectangles narrow, you can use this to sort of define integration, to say what's going on. All I really want to say is that I think this area under the curve is less than that area to do with the rectangles. Hello, I'm late, what's going on, says somebody. Nothing's going on yet. So far I've just drawn the graph 1 over x, and I've also drawn some rectangles on using the values of the function to give me the heights of those rectangles. Okay, so this is one thing I can do. This gives me an inequality that I could write down, I suppose. My inequality works like this, and the area under the curve, which, by the way, I can use integration to write like this, is less than the area of those rectangles. Okay, that's pretty nice. And maybe this comes up in A-level further maths, says Ali, maybe. Cool, okay. This is pretty nice. This relates together some sum of some values to do with the heights of the rectangles. Each rectangle's got width 1, so the heights kind of relate to the areas. Versus this integral of 1 over x from 1 up to n. And I know the area for the rectangles is bigger because the rectangles are all taller than the graph. The graph is decreasing, so I've taken the kind of left points here. Good, okay. So that gives me some relationship between this nice sum and this integral. This sum is semi-famous, 1 plus 1/2 plus 1/3 plus 1/4. It's called the harmonic sum. Harmonic because fractions 1 over something are sometimes called harmonic fractions, I think. So this is called the harmonic sum. And it's big. It's bigger than this integral, 1 over x from 1 up to n. Yes, harmonic series. Yeah, how are we going to find that sum? Well, exactly. So at the moment my sum is just the heights of some rectangles, right? I've just drawn some rectangles of the appropriate heights, like a bar chart of the sum, and it's big. It's bigger than what I would get if I integrated that curve. So side note, and you learn this at some point during A-level maths, I think. Not in the first half of A-level maths. So if you're studying maths and further maths in parallel, then you haven't got to this fact yet. But there's an amazing fact that this thing here is just log base e of n, which is a really good fact. It's just log base e of n. And there's a message about joint honours in there as well, which one gives the strongest mathematicians. They end up doing the same maths exams for their maths courses, as a point of comparison, I suppose. But I don't think there's any particular pattern. If you're a strong mathematician, then it doesn't matter which of the courses you're on because you'll learn the same material. Yes, it's like the rectangle rule for integration. If you can use this to sort of approximate the integral, if you make the rectangles narrow. Is that what people mean by rectangle rule? Oh, messages are being ordered by popularity. Thank you. Cheers. Preference in chat for lun x. Please thumbs up that comment if you would like me to write lun x instead of log base e. I never know what people find confusing. Okay, at some point in A-level you learned that there's an expression for this integral in terms of logarithms. It's log base e of n. A cool fact is that log base e of n gets really large as n gets large, slower and slower, but it does go to infinity. So that means that the sum on the right hand side must go to infinity as well. Log base e of n gets really big, so this sum gets really big. Even though the terms are getting smaller and smaller, 1 plus a half plus a third plus a quarter, adding on less and less each time, even though the terms are getting really small, if I keep adding terms on forever, then that sum gets larger and larger out towards infinity. Oh, here's a vote for the opposite, so if you want that, then vote for the opposite now. Well, hang on, that's got more votes than I thought there were people here. Oh my word, hello. More people have joined us. Hi. Good, lovely. Yeah, so Owen's got a way to phrase this in terms of n tends to infinity. I was trying not to phrase it in terms of n tends towards infinity, because I think I learnt that notation at university. So this stream is mostly people I think not at university. But yeah, you could say that as n tends to infinity, as n gets really big, there's no finite limit for that sum on the right hand side. Yeah, so it feels like maybe feels like the sum should converge to something nice like e or something, but in fact it doesn't. It just keeps getting bigger. Oh, have you seen n tends to infinity on your further maths course? Okay. Well, maybe I can get away with a little bit of that then. This doesn't have a limit as n tends to infinity, so maybe it's not the best time to bring the notation in now. Something that feels true, but is not obviously true, that I want to try and get to now, is that these things grow at the same speed. That's not obvious yet. So far I've just told you that one's bigger than the other. But in fact these things are about the same size. That log base e of n is actually a good measure for how big that sum is, how fast it grows. Yeah, we're not exactly learning. I think they meant A-level further maths. Maybe that was my assumption when people say further maths. Ah, right. You have to do Hospitalis. Oh my word. Okay, right. I think this is not the day where we learn about limits. I saw a request in chat for this to be the day that we learn about pasta as well. Which I've now got the camera, so maybe we'll see. You did mean further maths. Good. Yeah, it was me. And maths. You still can't write maths in chat. Sorry, even with my new system. Okay, what was I doing? I'm going to try and prove that the sum grows at the same rate as log n. That's not too hard. I'm going to do this with more rectangles. Let's pick a different colour. Okay, so new rectangles. Oh, this is an important chat message. What about the cabbage problem? So I've been teasing the cabbage problem for a couple of weeks, and then we tried to do it last week with the tech issues. Actually, the cabbage problem was then broadcast last Friday. So we missed the stream last Thursday, did a bonus stream, did a replacement stream on Friday, in which we talked about the cabbage problem. So if you want to see the cabbage problem, it was last week, last episode. Just not 168 hours ago. What is this Quora link? Okay, if you're in Vivox, there is a Quora link for people talking about logarithms. Good. Oxford's not responsible for the content of external links, etc. Okay, so I can take some shorter rectangles. Do you think I should do more legal disclaimers? We could do more legal disclaimers if you like. Any opinions stated on the live stream are opinions of any. Right, there we go. Right. Yeah, there was a live stream last Friday. This is episode 6 now. We did episode 5. After it got cancelled for internet trouble, it turned up the next day. That was a fun time, wasn't it? It's on this YouTube channel. If you're on the YouTube channel, you can get all the previous episodes. There are now about 40 of them. Goodness me. New rectangles. And I've switched to a rather attractive pink colour. I'm going to lose the title, but there we go. Okay. Hard question, what's the height of these new rectangles? So, I think this one, now I'm taking the right-hand side. So this first one is height 1/2. The next one looks like 1/3. And that one looks like 1/4, and so on. And the last one is 1/n. And that is smaller than the integral that we've got here. Let's check the votes very quickly. What are we voting for? Change his opinion. There we go. Good. More Lego. Yeah, good. Hi to Alfie. Sorry, I've got behind the chat as well. What's an integral? MathWorld link as well. Yes, it's the same harmonic series, -1, but add a little bit on the end. People have still got opinions on log x in chat. This is good. Yes, good. Brilliant. Love it. Good. Okay. Good. Okay, so I've got a very similar looking sum, but this time it's small. This time it's smaller than ln n. There's a separate question about whether you say log or ln. So I think I got to the point where I was writing this, but saying log out loud, and that really annoyed everybody. So I've learned to go with whatever chat says. I think chat's winning club. Missing a mod this week. It's also getting really near to exams, so it's just me today again. Ha! Good times. Right, good. Okay. What does this mean? So this says something like, this is missing the 1 on the front, so if I'm interested in the sum with a 1 as well, I could add that in. I'm going to write it in blue, which is a little bit confusing, but there we go. I'm going to add 1 to each side. And hey, here's the sum that I was interested again, that thing that's going off 1 plus a half plus a third plus a quarter plus all those fractions, and that's smaller than log base e of n plus 1. Maybe I'll say it a different way each time. That'd be good. Yeah, something bad about the word lund, right? Lund, like Lundy, or anyway. Okay, so this is good. This is now bounded that sum. Okay, small technicality. This one stops at 1/n-1, and this one stops at 1/n. But those are very similar. Those have got a very tiny difference compared to the enormous size of ln n. So really this sum lies between, on the one hand, log n, and then on the other hand it's less than log n plus 1. That means it's really quite close to being log n. That was where you were on holiday. I did not know that, Darishli. That's not me being creepy or psychic. I promise. Right, good. Okay. There is a question, I suppose. You know, this sum is really close to being the same thing as ln n. It's somewhere between ln n and ln n plus 1. What does it actually tend to? And when you learn about limits at university or something, you find out that it doesn't really make sense to ask what it tends to, because it tends to infinity, it gets really large. But what if we subtract off the log n? Does that tend to a constant instead? And in fact that does. And that constant would be the areas that we found, the little areas of these shapes above. That turns out to be 10 to a constant. Yeah, so there's a chap person in here has suggested the sum from up to 1 over n is greater than the sum from 1 to n minus 1, but only a little bit, only because it's got this extra term at the end of 1 over n. That's really small for large n. In the limit, that's way smaller than this adding 1 on that we might be interested in. So I have brushed something onto the carpet there to compare these two sums. We've shown that we have shown, you're correct, this is a correct conclusion, by the way. We have shown that log n is less than log n plus 1. So that's alright. Yes. The question that Dirichlet is answering in chat is, what's the constant in between? What does this actually tend to? And this is kind of weird-ish result, I suppose, that this sum, how am I going to write this? I think I'm going to write that the limit, let's put a limit in. We can handle a limit, I think. Just one. You should read this as the limit as n tends to infinity, or for short you could just say as n gets really big, of 1 plus, so brackets around this bit, to show what I'm taking the limit of. But I'm going to subtract off that log base e of n. This thing, maybe surprisingly, this is a constant. This does tend to a constant. The constant is about 0.577, which is called sometimes Euler's constant, or sometimes called the Euler-Mascheroni constant. Apologies to Mascheroni, I do have to look down to work out my notes to work out how to spell Mascheroni constant. It's some number, somewhere in between 0 and 1. Ooh, somebody's pasted loads of the numerical value into chat. Possibly Dirichlet. Does the A-level cover all of the IB curriculum? I'm not sure. I think IB curriculum includes some slightly different maths topics. I think it does things slightly differently. The syllabuses, well, the syllabuses are just slightly different, but not in a very important way, if that makes sense. Do not stress about the differences between A-level maths and IB maths. They're both great. This is quite good, that there is some sort of constant out here for the difference between this sum and log n. It's maybe a little bit surprising that there is such a constant, that there isn't some weird function of n over here as well for what that difference is. Maybe the one that depends on n. And never mind. People are now pasting different bits of the Wikipedia page. I think that might be the Euler-Mascheroni constant in binary, perhaps. Either that or it's some sort of message in binary. I'm actually going to take it off the screen just in case. Yeah, and we don't know whether this constant is irrational or not. Dirichlet's all over this, which is sort of amazing that it's quite a simple idea, but we don't know if it's irrational. Unsolved problem. We think it's probably irrational, if that means anything, right? That if it's rational, then if it could be written as P over Q, then we know that Q is enormous. But that's not actually proof, and that's not a proof on its own that the thing is irrational, but it really feels irrational. Also because it involves this logarithm, which makes me feel like it should be irrational. That's not how the things work anyway. The numbers worked out, I suppose you could work it out from this definition by working out a huge sum. So put n to be some really big number, work out this sum and subtract log n. That would give you the constant to some number of decimal places very, very slowly. I think you have to set n to be 1,000,000 to get even a couple of decimal places out of this, to get your computer to do the adding for you. But you can use that to calculate the constant over here. As you increase n, it gets better and better. there are more efficient ways because there are other things, there are other expressions that the Euler-Mascheroni constant, other places where it turns up. A bit like how pi turns up in lots of different places, so there are some ways of calculating pi that are more efficient than others. There are other ways of calculating this constant that are more efficient than others. I'm not going to get sidetracked. What stops us from proving it? Yeah, good question, I suppose. Why don't we just finish off all of maths, right? We know what the question is. Is this number p over q? Step 1, suppose that it was equal to p over q. Step 2, I don't know. It's a sort of surprising truth, really, that some maths is just difficult. It's very hard to tell by looking at the question which maths is maths you can do straight away, like proving that root 2 is irrational, and which maths is maths that you can't do straight away. I was going to prove that it was bigger than 1/2. I think I might do that now. Yeah, Dirichlet agrees with me. People are talking about GCSE maths. Did someone dox themselves? I don't think they doxed themselves. Yes, there's a bit of the problem. As n gets to infinity, ln x, log x, is really big, but that's okay. The sum is really big as well. These things are both massive, but they sort of cancel out a lot. So if you add up all of these fractions out to n equals 1,000,000, you get a really big number. Log basically of 1,000,000 is also big. Not that big, really. You subtract them and you get something that's between 0 and 1. And this person offers to, in exchange, I did it by mistake. This person offers in exchange, no, there we go. It's funny, I want to publish it, there we go. In exchange, I give them admission to Oxford. They give me the proof of this. Okay, cool. I'm going to prove it's bigger than 1/2. I wish I hadn't already told you that it's 0.577. That's really, ruined the dramaticness of this next bit of proof. But we had that question about how to calculate it. Yeah, okay. Infinity take away infinity equals 0.577. Sort of, a bit. I'm not going to let you do the separate limits. So limit of this whole thing with the brackets works. Limit of just this first bit doesn't work. You can't always split things up like that. Yeah. So everyone in chat is supplying the proof. 0.577 is bigger than 0.5, therefore proved. But how do you know it's 0.577, right? I told you, and maybe you shouldn't trust me. Oh, but now you do have to trust me when I show you this proof. Goodness, that's rather confusing, isn't it? Let's just do the proof, and then we can talk about trust another time. So this was using the area of rectangles for to do things with the integral, but I would like to think about instead using the trapezium rule. Let's see. Algebraic proof is better than numeric proof. I will say numeric proof, you've got to know that your computer might currently be giving you numbers that are bigger than 0.5. How do you know? If you keep going for larger n, it might start giving you numbers that are smaller than 0.5. Computers are tricksy like that. As n tends to infinity, lots of different things can happen. I've written trapezium rule on the board to give you a chance to think about what the trapezium rule says, and a chance to remember what the trapezium rule is. Yeah. Also, okay. Here's an argument. Log n. Let's analyse this. Log n is always irrational for an integer n, and the harmonic series is always rational when stopping at any point. So it's irrational. Does it break down in the limit? Yeah. So rational and irrational doesn't pass through the limit like that. So you're telling me that the sum of the harmonic series is a rational number for all n. That doesn't mean that the limit. I mean, the limit doesn't exist, but it doesn't mean that the limit would be rational as well. You can have a series of rational summons, rational things that get closer and closer to an irrational number. For example, okay, side note, maybe just for SV, sorry, 3 plus 1/10 plus 4 1/100ths plus 1/1000 plus 1415, this thing. This is a sum. I can keep putting extra terms into it. As I keep putting extra terms in, I always get a rational number, but it's getting really close to the number pi, because that's how I'm choosing the digits to write down. So this is another example of rational things being added together that actually gets closer and closer to a famous irrational number. You can't pass rationality across limits. What am I doing? I'm doing the trapezium rule, and people are already working out what's going to happen with the trapezium rule. Math prep advice while we're thinking about this. So math prep advice. Math's based on a very limited syllabus. When it comes to doing the Math live stream starting in August, we're going to spend a bit of time on the Math live stream, if you watch that show, going through the syllabus maths. You can get a head start by downloading the syllabus from the Math website and having a look at what is on there and whether you've already learnt it. Yeah, so is the rule in year 2? If you're doing maths across 2 years, then you haven't seen the integral of 1 over x. That was a new fact for you to learn today. Haven't seen the trapezium rule yet. So when I said you hadn't learnt it yet, then that might be a bit unfair. When I said you haven't remembered it, that might be a bit unfair. Yes, good. Okay. There's no way to type LaTeX or MathJax into chat. Some people have got special keyboards that let them type emoji. Oh, and SV thinks the trapezium rule might be in GCSE, which is embarrassing for me. It's also not used. Trapezium rule used to be on the Math syllabus. Talking about the Math syllabus, trapezium rule used to be there, is no longer there. I'm going to try and draw what the trapezium rule says. It says, if I use trapeziums instead... Oh, there we go. These are some pretty good trapeziums. So these are trapeziums. They've got a left side, a right side, which are parallel, and they've got a top that's not parallel to the base. Trapeziums. Trapezia? Let's not have that argument. Let's call the whole thing off. Okay. 2 years for both maths and further maths. Yeah, okay, Durishla, here's a question. Can irrational partial sums converge to a rational sum? The answer is yes, and it's not that hard to work out an example. Yes, a plus b over 2 times the height, but that my trapeziums are sideways, so the height is going to be 1 for that width. Is there no trapezium rule for IB mathematicians? We're getting back to that discussion about IB and maths. Right, okay. Hopefully you know how big a trapezium is. If not, you know how big a triangle is, and you can work out how big a trapezium is from there. Here the rule is going to be that this purple area of these trapeziums, maybe I don't even need to call it a rule for this. It's 1/2 times the height of the trapezium. My trapeziums are sideways, so the height is 1 times, I suppose, 1 for the first height on the left here. 1 plus 1/2. Plus 1/2 plus 1/3 for the next trapezium over, plus 1/3 plus 1/4 for the next trapezium over, plus and so on and so on and so on, plus 1 over n minus 1 plus 1 over n. Okay, now the trapezium rule, the idea here is this is giving us another expression for an area. This one, I claim, is bigger than the area under the curve. I think we should have a moment to think about why that is. I'm going to claim this. So that area under the curve is still log n. Everything base e today. Yeah, so the trapezia overestimate on this example because 1 over x curves, let's see if I can get it to curve the right way on the screen, curves like that. It's a convex function. Yeah, not just a decreasing function, because it could be decreasing like that, like a concave function. The fact that it's convex. I've been saying convex, and someone in chat has just said concave, which has made me really worried about the words convex and concave. I mean, it's curved upwards. Its second derivative is positive. Okay, so slightly calculus themed arguments to say that this is curved up like a bowl. As the second vote in chat for the word concave. We're going to call this a concave function, concave upwards. Yeah, there was a question about step and Matintima, which someone else has answered. If you're 11, then none of them are right yet. Oh, now I've got two votes for convex as well. That's looking good. Okay, good. Right. Anyway, the lines for the tops of the trapezium are on top of the curve, so the trapezium area is bigger than log n. I've written on the side in quite a funny way because I've added together all these trapeziums. It's basically two copies of the sum that we're interested in, except it's missing an extra 1 inside here, and it's missing maybe a 1 over n inside here. I can add those back in, I suppose, to say that this thing, if I add on 1/2 to both sides, then I'll get. So I'm gonna. This is 1/2 of 2 halves, 1/2 of 2 copies of 1/3, 1/2 of 2 copies of 1/4. Everything is kind of sensible and nice. I need to add on that bonus 1 over 2 and a bonus 1 over 2n. I keep going under chat, there we go. Okay, so this sum is bigger than log base e of n plus 1/2 plus 1 over 2n. Oh, yep, more votes for convex. More votes for concave. So I learned that concave is the one that looks like a cave, which a bear might live in. But convex is the one that a bear wouldn't live in. It's been vexed by the upward curving nature of the shape. We're trying to prove that Euler's constant's bigger than 1/2, which I think we've now done. Because if I subtract this logarithm from both sides, then on the left I'll get the definition of Euler's constant, this sum minus log base e of n, and on the right I'll get something that looks a bit like 1/2. So I'm going to write that out. I'm going to write some limits again. I've decided that I'm into it. We're doing limits today, in the sense that I'm making this argument about what happens for very large n, and it's happening. You've got to subtract the logarithm first. I've gone under chat again, haven't I? Can't help going under chat today. There we go. 1 vote for concave x. That's just 1/2. So as n gets really big, oops, capital N today. As capital N gets really big, this gets close to 1/2. But this thing on the left is just the Euler-Mascheroni constant. So it's bigger than 1/2. Hooray! Which I really ruined by telling you the value of the constant. So the 1/2 on the left, yeah, I did this quite a little bit too fast, didn't I? So on the 1/2 on the left, I've imagined multiplying out the bracket. So there's 1/2 of 1. I then added 1/2 to both sides in a confusing way, and then I took 1/2 of these two terms to give me this, 1/2 of these two terms to give me this, and 1/2 of these two matching terms to give me this 1/4. So I sort of allowed for the fact that there are 2 copies of almost everything inside that balances out the 1/2, except I need to add on an extra copy of the thing inside here and the thing inside at the end. Seen the shape of the thing before, so the shape of the trapezium rule before, so I kind of knew that the first and last things were a little bit different. That's why I added on the 1/2. The trapezium here is the average between. Faster argument. The area of the trapezium is halfway between the area of the pink rectangle and the blue rectangle. So I could have just written down the average of these two sums, which gives me 1/2 at the start. Good. Because trapezium it slopes, right? So it's like a little triangle at the top. Let's draw a little slow motion replay of that argument. I've got 2 rectangles with a trapezium going through the top. So the bottom rectangle plus half of the area above gives the trapezium, so I should have just averaged my 2 rectangle things from before. But where's the fun in that? Good. Can I use a similar idea to get an upper bound for the constant? That's an idea. So I'd need to draw some lines that are some some lines that are underneath the curve. Yeah, okay, I need to draw some lines that are underneath the curve. Maybe, I'm wondering whether I could... This would be a lot of work. I think I'm not going to do this now. But one idea is that I could draw some tangents to the curve, maybe at the midpoint. Draw some tangents and use that to give me some trapezia. And then I've got some lines that are underneath the curve, and I can add those up because I know how big trapezia are. Probably, I think I can get away with that. And I'll get something that the area is bigger than, and that'll tell me that logarithm is big. It's bigger than some trapezium sums. Actually, working out those trapeziums, I've got a little bit nervous because I'm gonna have to do a lot of sort of A-level maths to work out what those tangents are and what the heights of the trapezium are. And suddenly, you know, when you have an idea and you start out and then you're no, there's a reason why this is going to be complicated. One of those moments. Good. What's the use of the Euler-Mascheroni constant is a perfectly valid question. It's sort of like asking what the use of pi is. It's just a constant that turns up in quite a few different places. We can't stop it turning up when it turns up. If the answer to your problem is this number, then I'm sorry, that's the answer to your problem. It turns up in, I suppose, no, I think there are quite a few integrals where the answer is related to this constant. A bit like how knowing about pi lets you write down the value of several integrals that might look unrelated to anything to do with pi. So knowing about the value of pi lets you write down, for example, the value of this integral as being exactly pi over 4, which is a little bit surprising. Definitely the first time you see it, it's very surprising. Just like if you know pi, then you can write down facts about this integral. There are other integrals, more complicated perhaps, where the answer might involve the Euler-Mascheroni constant. So it's just good. We've worked out quite a lot of decimal places of it, so it's a known quantity in that sense. It would be quite nice to know whether it's rational or not. If it's rational, that would be great, because then we could calculate all the decimal places. Some physics undergrads say they get PAT close to full marks if they took the PAT now. Right, confident people. Teacher in maths at Cambridge and struggles with the mat. That's mat is supposed to be quite a hard test. So is PAT though as well. I think the physics undergrads are being very confident. Maybe they would do. Maybe they would do well on the PATs. PAT and maths are quite similar as well, so I'm not sure there's a difference there. Do I think I pi is the logarithm of -1? I think that's one of the values of logarithm of -1, but there are others. Yeah. So other integration techniques are available that you could go and have a go at. Is it equal to e? No, it's different constant. Same person, Euler. Same idea of writing down a constant, different constant. You know you've made it as a mathematician when you've got two different constants with your name on. Yeah. I haven't been using sigma notation on my sums today because I don't think it will be very helpful today. It makes things quicker to write and shorter, but I'd also have to explain what was going on. Trapezium is from, right, this just in from etymology corner. Trapezium comes from Greek, so not trapezia. Trapeziuses or trapezii. Wow, thank you etymology corner. I've no idea if that's true or not, but it looks exactly like other etymology facts. How does floating point addition work in? How does floating point maths work in C? You can find that out, right? You can work out how you can. That's the sort of thing that you can just find out, I think. C has got some rules for how it works out cosine and sine. There's some surprisingly cool tricks in there that we're not doing now for how you efficiently calculate cos and sine. You can do a polynomial approximation if you want to, but there's slightly better methods. Anyway, I got distracted. Good. Request for Ramanujan summation, but I've also got this request for the pasta book as well. Let's see if we can look at the pasta book. Can I look at the pasta book? I'm going to try and set up the pasta book. this is a bit too ambitious, maybe. The Wikipedia page on Euler-Mascheroni constant has got lots more applications of stuff going on. And people are quoting the 3 blue, 1 brown thing, where if there's pi, then there's probably a circle. Let's invent our own version of that statement. If there's an Euler-Mascheroni constant, then there's probably a logarithm. There we go. Eat your heart out, Grant. Good. Yeah, so I saw a really good article on, was it, I can't remember where I saw it. I can't remember where I saw it, but I saw a great article that explained what calculators are actually doing when they're working out cosine. There's some really nice algebra for it that I saw an article on once, but I can't remember where it was. Right, yep, watching chat as well, also trying to set up pasta book. Oh, we had a request for the pasta book so long ago. I think Harriet's been really keen for the pasta book ever since. I'm trying to plug in a camera that will let me display the pasta book. Is this going to work? Oh, come on, pasta book. Yeah, okay, that's going to work. That's going to work really well. Okay, 2 seconds. Is that... Oh, right, okay. This Wikipedia link looks really suspicious, but I checked it. It is a Wikipedia. Is it Wikipedia? Is it a Wikipedia thing? Yeah, when are we getting Grant on the show, right? Okay. So, fans of the stream know that there's ages ago, like I think last term, we had a quick look at a book that I have that we later found out is almost impossible to find on the internet. So I thought I'd show you some of the contents of that book. Let me do that now. Here we go. Whoa. It's Pasta book. So the book's called Pasta by Design by Georges Legendre. It's really good. It's out of print. I got it about 10 years ago. The idea of the book, you can kind of see on the cover, is to write down equations that, when you plot them, give you the shapes of different sorts of pasta. Yeah, so there's one, in this way that sometimes books turn up on Amazon weirdly expensive. There's one copy on Amazon that's weirdly expensive. I really don't think anybody should try to, there's a link in chat, but I really don't think we should try and get it. Okay, right. If you can find that. Oh, it's also put a maths challenge in here as well. This is unrelated to the Euler-Mascheroni constant, but I wanted to show you some of the pasta in this book, just to give you an idea. People in chat I've seen are quite keen on calculating using Desmos and things like that, so challenges to use Desmos to draw things that look like pasta. Here's one that I like, so here's Linguini, Linguini by Georges Legendre. So you see that you get a little plot of the author's functions, and up here there's some equations. They're using cosine and sine to describe the kind of elliptical cross-section of the linguini, and then this big K over here is just J over 5, or some expression for going along the length of the linguini. The idea for all of these is that the author's written out some expressions in terms of integers I and j, and then they're plotting points for different values of I and j, so that their computer produces these plots of different points. Linguini is not the most exciting shape of pasta. So I've heard that, yeah, Amazon Books, I've heard that there's some automated, right, so there's like some machine learning problem, or even stupid machine learning, where you just price your book on Amazon. If you're selling books, you list the book, picking somebody else's listing on Amazon, but add a little bit of money, with the intention being that you can buy the book from them and then sell it. If you write a computer program to do that, then you'll list all the books on Amazon, slightly more expensive than everyone else, but maybe you can use dark arts of the internet to make sure that your links get hit first. If you have two people doing this, then what happens is a sort of feedback loop where they're both pricing their books higher than each other, so every time their code updates, it lists the books for more and more money. Good, right, okay. I think this is fair use. I'm being told that it's not fair use. Let's have a look. Matt Parker did a video on this. I think it's fair use. I'm encouraging people, I think, that this is a really good book. And it's possible that somebody's going to buy that copy on Amazon for about £1 million, which I suppose I did say that was not a good idea, but hey. Farfalle is quite fun. They've done some great work here to try and calculate the shape of Farfalle, which I think is really exciting. They're quite keen on different powers of sine and cosine, which is really good fun. Mostly I think I'm trying to celebrate how brilliant this author is. Georges Legendre, once again, shout outs if they're in chat. And I also wanted to show you my favourite one, I think, just to respect the incredible amount of work that went into this. I wasn't even aware this was a sort of pasta. Can you see this is a sort of pasta that looks like tennis rackets? It's called rochette, and look at this. They've done so well here. Recreate that in terms of just equations to explain the shape of that bit of pasta. I think that's absolutely fantastic stuff. So the book's called Pasta by Design. It's out of print. There are a few copies on the internet, but goodness me, those are expensive copies of books. Good, right, okay. Matt Parker's done a video on book pricing. Yes, good. What is it for? Yeah, who knows. I think it's an exercise in parameterizing things. We had an episode last term where we talked about parameterizing different surfaces, which is what these pasta things are. This trying to parameterize the surface of the pasta. People are putting YouTube links in chat, which always makes me nervous. Oh, that's the link to the Matt Parker thing. Good. Okay. It doesn't actually help you make pasta. There aren't any recipes in there. Oh, it's a second link to the same thing. Good, thank you. Good. And someone's eating pasta in chat right now. I thought vaguely that it might be interesting to do one more variant of this summation thing that we had going on, because we've talked about 1 over x and how you can add up 1 over x to get facts about this sum for 1 plus 1.5 plus the third plus a quarter and so on. But there's nothing to say that we have to use this particular function. I started the live stream by drawing 1 over x. Something you can do instead, let's do some suggestions here. So I think if you use y equals 1 over x squared instead, you can get bounds. So bounds like an inequality on the sum, and I will write this one out like this, 1 over n squared. So that's kind of cool that this one, if you have 1 over the squares of numbers and add those up, that one is bounded, and you can prove that by adding things up. So that you can prove that with the rectangles on 1 over x squared as well. But I think something that's fun as well is that you can use other ones. Yeah, I did see the personal statement question and the emission stuff, but I was in the position of holding a pasta book at the same time. Instead, for goodness knows what, something else. Something I like to encourage people to do. Let's relate this back to admissions then. Something I like to see people do when it comes to personal statements or just getting ready for maths at university is to explore a bit more, to just try out messing around with different things that are going on. So here I've shown you that you can use rectangles and functions and thinking carefully about what integration means to get bounds that relate together integrals and sums, so that this sort of mysterious sum, the harmonic series, has got really something to do with the logarithm. The best way I know to discover that is by thinking about integration. I know that URL. So something that you can try is other functions, which probably give you other results. Really, there's a technique hiding in here that's a sort of inequality factory for generating new inequalities out of your choice of functions. I've got some suggestions on the board, but you might like to try just sticking a different function in entirely. I could suggest things, but I suppose the point is that you can think about other things as well. 3D Fourier series, ha ha ha. What pasta do I like? Oh, I'm quite basic. I like the massive pasta shells. Is that basic? The normal pasta shells is one of the normal ones, right? As I was saying it, I realised I like the massive ones as well. We're not going to ask about pasta at interview. People literally write, I messed about with this maths on their personal statement. I mean, I did a bit. I wrote about some stuff I was interested in and I'd messed around with a tiny bit. In hindsight, the maths that I messed around with was not original and not very interesting and not related to university maths at all. But I still think it was good for me to have tried to prove. I was messing around with sort of dice problem. We had a bit last year where I talked about dice problems, maybe too much. And one of them was something that I was interested in when I was thinking about applying for university. Ooh, yeah, okay, cool. Challenge in chat as well. Prove that this thing isn't a square unless it's 3. Apparently using some similar technique. Yeah, James on my first. Yeah, this is a quote from my personal statement. I've tried to prove something, but I have not proved it. And I've tried to read a book, but I failed at that as well. Which is an accurate summary of my personal statement. My personal statement is somewhere on this YouTube channel as well. It's got a terrifying number of views. In terms of, it was terrifying when it had 100 views. I do not recommend putting your personal statement in a place where over 100 people can see it. That's a scary number of views for your personal statement to get. Oh, is that a promise question? It's a promise question. I thought it looked familiar. Losing sleep on it. There's some promise questions out there as well. I should have recognised that faster, I think. Having encouraged people to do stuff. So I did skip some admission stuff while we come up. Can we do it an hour and a half instead? When it comes around to Matt livestream, Matt livestream's going to be longer. This one is stopping at about 5 o'clock, I think. Can I recommend any stories for my? Can you recommend any stories for my personal statement? Says someone up here. So stories like books, like there are some books recommended in the prospectus for the maths department at Oxford. If you search for something like Oxford Mathematics prospectus, then halfway down there's a list of interesting books. I don't know about stories. I quite like the sort of storytelling that, the way 3 Blue 1 Brown videos work, that they sort of tell a story about solving a problem from the beginning to the end. There we go. And yeah, one recommendation for Harry Potter at the same time, a Terry Tao book and a Harry Potter book at the same time. So I missed this one. An anonymous person is working on writing an audio compression algorithm. I can't read words. An audio compression algorithm using Fourier series. That sounds really fun. It doesn't matter in terms of Oxford admissions or something. It doesn't matter whether the algorithm works or not. The interesting thing to cheaters at the moment, I suppose, is that you're messing around with something. I'm using messing around as a shorthand here for all that kind of serious, essentially research that you're doing to work out what a Fourier series is and how audio compression might work. And it's probably exposing you to the sort of ideas that you might meet again if you study at university. I think we're talking now a little bit about solving a promise question, which is fine, but I haven't tried the promise question. What is Cambridge pre-U? It's an exam. It's a qualification. Do we favour it? No, we consider it equivalent to A-levels. It's also not going to be examined after next year, I think, possibly. Oh, don't quote me on that, and it's irrelevant. I think at least in some places it's not going forever. If you're doing Cambridge PU, should I state that I did Cambridge PU maths in my personal statement? You will state it on the qualifications section of the UCAS form because it is a qualification. How do you show to university that you have a passion for maths? I'm on the fence about the word passion for maths anyway. If you're extremely good at solving maths problems, then essentially that's good enough. We've got loads of maths problems on the maths course at Oxford, and if you can solve maths problems, then that'd be pretty good. I have no GCSEs or equivalent, that's fine with me. Only A-levels, that's fine with me. Yeah, you can. A-levels are sufficient preparation. If you've done maths A-level and preferably further maths A-level, if it was available to you, and that sounds like sufficient preparation to me. Normally GCSEs or equivalent or something like that is necessary in order to do the A-levels, but everyone's different. Do you put all your exam results on your UCAS form? Yes. This is a UCAS rule, not an Oxford rule. You put down everything, including your previous qualifications, or I suppose exam results as in qualifications, not. You don't have to put down the detail of I sat 3 papers for this exam and they all went well. You put down qualification results. Maybe that's different from exam results. Qualification results, and you put down any qualifications not yet completed. Wow, 8.8 at GCSE is amazing. That's really good. That's incredible. I think 8 and 9 is roughly equivalent to an A-star or something. Goodness me. And there's advice about applying. Oh, hang on, for IB. Yeah, that sounds all right. The standard IB offer is 766 at higher level and 39 overall, including 7 in mathematics. So that sounds to me. I'm old enough that my GCSEs don't use any numbers for what I got, but there we go. Lots of people ask me this sort of thing. If you don't have any competition rewards, is it okay to apply for math major? Yeah, it's fine. Competitions are not for everyone, and they use slightly different maths compared to university maths. So they are kind of slightly separate from the stuff we do at university. If you're really good at maths competitions, then you're probably really good at solving maths problems and probably really good at learning university theory and doing well in A-level exams. So in some sense, all these things tend to go together in the same people sometimes. But there's also loads of people who don't have any experience of doing exam are doing other competitions. What do you need to know for math beyond the AS math syllabus? The answer to that is geometric and arithmetic progressions. You're not expected to know that by me telling you here. There's a syllabus, it's 1 page of A4, there's a syllabus on the math page. If you search for Oxford Math Syllabus, then I really hope that my website comes up top and you find the Oxford Math Syllabus, which has got some AS maths and then just a couple of topics from A2 maths. It's not called A2 maths anymore. Yeah, like UKMT is a thing. If you've got access to UKMT stuff, then give it a go. It's there. The UKMT sets math challenges and things that you might enjoy, you might not. But it's not a prerequisite in order to study at Oxford. Not everyone does them. Cool. How easy should a potential mathematician find the IB Maths course? There's some challenging stuff in there. It's got a lot of stuff, and you study it over the course of about 2 years, so enough to keep you busy for a couple of years. So by the end of the course, you should be quite good at the IB Maths material. I think it's safe for me to say. But the process of learning maths is tricky stuff. Jerusalem's studying Imperial in October. There you go. I think Jerusalem's mentioned before you're on like a gap year sort of thing or something. I think that's right. I can't really remember. Good. Cool. Sorry, I feel like piecing together these bits of people's lives. There we go. 8.8 was really good. Did I say enough that 8.8 was really good? It was almost like, it's borderline. It was almost like showing off. I thought it was this close to showing off. Because 9 is the top, and we all know that 9 is the top. Do you put U, Q, and X? Oh, I've never heard of X, sorry. On your UCAS form? Yeah. I've never heard of X. I should know more about A-level grades. I know about U. What is that? Somebody else has got a hash sign in their A-level results. I've never seen that before. Sorry, can't help you. Wow, I'm learning a lot today. If you've done UKMT, you can talk about it on your personal statement if you like. Yeah. First mat attempt. I'm going to leave that for chats or something. 45 for predicted score. That on the IB, you said this is very, very close to showing off, right? Because 45 on the IB is the top score on IB. So other places Euler-Mascheroni constant turns up because we've got a request. Oh, I wrote one of them down. I really struggle to remember these. This is the kind of simplest integral I could find. It's minus 0.577. Integral of e to the minus x log base e of x. Log base e of x. There we go. That integral is minus 0.577. I think that integral might be easier to work out than the sums. So if you can do this integral with a computer, with the trapezium rule or something, I guess, if you want to, then there you go. Oxford and Cambridge maths are both amazing. If you're interested in applying to either of them, then things are clearly going pretty well. Okay, right, talking to Dirichlet. Dirichlet may have previously said something, blah 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 blah, blah 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 blah. Request for elliptic curves. Oh, elliptic curves are really tough and they're not my sort of maths. I might need to get a guest on to talk about elliptic curves. Pretty good, pretty good. James, when he finds out there's grades below A star at A level, shocked Pikachu face. This one just told me that you can get a hash, and I at first I thought that they mean like an A hash, like some sort of amazing A hash grade. IGCSE students following the A star to G. Oh yeah, we think A star is roughly equivalent to an 8 or 9, and we think that at the moment we think that 8 and 9 and A star are all about the same thing. We didn't have very much data on the difference between 8 and 9, and then there was a pandemic, and that made all of the data pretty noisy, so I still don't feel like I've got enough data to say that. I mean, I know that 9 is a higher grade than 8 on GCSE, but I don't feel like I've got enough data to say what the difference might be. GCSE data's been so noisy for a couple of years now. This is nice. I'm now just enabling chat to talk to chat. So